This video is on using the standard reduction potential table, which I'll be calling the SRP table, to help us write a balanced redox reaction, which will give us moles of electrons transferred and also the um, electromotive force or E cell standard. And then based on that information, we'll be able to calculate free energy during a redox reaction. So I found if we follow these four steps that we should be able to solve any one of these. As long as we read, you'll find out. You'll see by the end of this that reading the SRP table is the most important thing. Is like the fundamental skill here. So like anything in redox, like anything in electrochemistry, this whole chapter, this unit, the first thing usually that you always want to do is assign oxidation states and figure out what's reduced and what species is oxidized. Once we do that, we can split them into half reactions. Remembering that, so when you split it into half reactions, the reduction side, the reduction half reaction, the electrons are on the reactant side because the reduction is gaining electrons, and that process of gaining electrons happens on the reactant side. So that means one of the reactants is gaining electrons. On the oxidation half reaction, the electrons appear on the product side. You'll see this is a critical component to reading the SRP table correctly, is to get the electrons on the correct side. Um, so then we apply oil rig or some other mnemonic. So oil rig is oxidation is loss and reduction is gain. And this just helps us remember, which species is gaining electrons and which one is losing electrons. So it helps us split the reaction up. Also, the other mnemonic is that a lot of students prefer is Leo the lion says ger, G-E-R, and this is the same thing as oil rig. It's just a different order. So it's loss of electrons is oxidation, and a gain of electrons is reduction. And again, these mnemonics just help us split the reaction up correctly and help us remember that concept. So the next thing you do, here's where it gets a little interesting, is you compare the half reactions to the SRP table and copy exactly what it shows. Um, and also says remember to flip the oxidation half reaction. So remember, this is the standard reduction potential table, so it's only showing things getting reduced. So as we know in redox, one thing gets reduced and the other thing must be getting oxidized. You can't have two reductions. That wouldn't make sense. So what this means, we'll see, I think will make more sense when we start looking at the examples in this tutorial, but it says copy exactly what it shows. So what this really means um, is to once you split the reaction up, so after splitting into halves, half reactions, just write half reactions. Just write as much as you can, and get the rest from the SRP table. And like I said, I think you'll get more of what that means when we look at an example, and then I'll come back to this slide to show what that means. So once you have the correct half reactions fully written out, then you look and see the total electrons transferred. So this is going to be N right here in our equation. So this right here is this right here is moles of electrons transferred once they're balanced. And this term F is Faraday's constant, which is 96,485 coulombs per mole of electrons. And E cell, of course, is what we get when we add the two half reaction voltages. And so this number is going to be in volts. So it's going to be volts. But we need to, when we use this equation, we need to put this in terms of energy. So 1 volt is actually 1 joule per coulomb. So you see when we use this equation, you're going to see that moles of electron cancel with moles of electron in Faraday's constant. And then this coulomb will cancel with coulombs here. And then once we plug everything in, we'll end up with joules, which is what we're solving for. We're solving for free energy, which should be measured in joules. So that's why when you write E cell, the volts have to be in joules per coulomb so that it matches with the other two variables in the equation. So let's see. Okay, so step 4 here is recombine the half reactions and then write everything as one reaction, and then cancel out any species that are in common. So basically, after step 3, we're pretty much done. But then in step 4, we just want to write out the whole reaction, and then you could write the line notation if you need to, and all those other things. All right, so let's start a example problem. So here we have iron reacting, so aqueous iron ions reacting with copper, and like always, the first thing to do is assign oxidation states so that we could split this up. So as we see, copper is a 0 here, and then on this side it's a 2 plus. So it went from 0 to 2 plus. That means it lost electrons. So and let's see, oxidation is loss, or loss of electrons is oxidation if you're using Leo the lion. So copper, and remember oxidation, the electrons happen on the product side. They need to appear on the product side. So we're going to write copper 2 plus 2 electrons. Um, Another way to tell that it should be on the product side is the balancing here. The net charge over here. So this is a way to remember that electrons should be on the product side on an oxidation half reaction. This is 0, the net charge, and then over here we have to add the 2 electrons to make it so that the 2 plus here balances with the 2 minus here, so that the net charge on this side is also 0. So that's a way you can double check that you have the electrons on the correct side, which will help us find it on the SRP table. The reduction half reaction must be the other species, iron 3 plus 1 electron, and then that makes Fe2 plus. So the next thing to do is to find these on the reduction potential table. So this is our oxidation half reaction. We will not find this as written here because this is showing it flipped. So what we're going to see on the SRP table is we're going to see this on the reactant side. This will appear on the reactant side, and this right here will be on the product side. I'll just write P side. So let's go ahead and try to find where that's at, what reaction that is. So here's my reduction potential table. And I see that it is, let's see, Cu2 plus. So I need to be looking for Cu2 plus and 2 electrons on the product side. I'm sorry, on the reactant side, and solid copper on the product side. So I think I found my reaction. It's this one here. So it's reaction 31 right there. And I need to change the sign here because this is actually flipped. So we actually have Cu2 plus 2 electrons. So the E-ox is going to be negative 0.34. So let's go back to our let's go back here. So E-ox is negative 0.34. And for our reduction reaction, we need to find this on our table. So Fe3 plus making Fe2 plus ions. That one is, let's see. Well, I know if this is going to be negative, and I know to get a positive E cell, it has to be higher than negative 0.34. So it can't be one of these. So I know I need to start looking over here, and I believe this is it right here, is number 25. Okay, so it's a positive 0.77, this one. So this is E red is positive 0.77. Okay, the next thing I need to do, so my next step was to split it and compare to the SRP table if you're following the steps from the last slide. SRP table. My next step is to balance the electrons. So I have two um, being oxidized here. So I need to multiply this reaction by 2 to make it balanced. So it's 2Fe 3 plus, and then I distribute the 2. 2 electrons makes 2Fe 2 plus. So I can go ahead and figure out my cell potential. It's going to be E red plus E ox, and so it'll be 0.77 plus a negative 0.34 or minus 0.34. So my cell potential is a plus 0.43 volts. I'm going to save this. My total electrons transferred is 2. So because I have 2 electrons transferred. Okay, so now I'm gonna rewrite my overall equation. So I have solid copper reacting with 2Fe 3 pluses, which produces copper ions plus 2Fe 2 pluses, and the electrons cancel out. As you see, we have 2 on the product side, 2 on the reactant side. Now I could calculate my free energy under standard conditions, negative. So this whole term is going to be negative. I have 2 moles of electrons transferred times 96,485 coulombs per mole of electrons times 0.43 joules per coulomb. So moles of electrons cancel, coulombs cancel, and then I get my answer should be limited by this number, which has 2 sig figs. This is an exact number, so that has infinite sig figs. This is actually measurement, so this would limit it, but I'm using actually 5 sig figs in this. So my answer should be limited by the 0.43. So if I calculate this, I get negative 83 kilojoules of free energy. Okay, so let's move to a more challenging example. So let's look at this one. All right, so as always, step 1, assign oxidation states. So this one is a 2 plus, the manganese ions. And here, we need to do a little arithmetic here to figure this out. So we have 4 oxygens, and they're -2 each, so that's a -8. And then overall, it has a -1. So that means this manganese here must be a 7 plus. So the manganese ion went from a 2 plus to a 7 plus. So it lost 5 electrons. This is our oxidation half reaction. So once we determine, we go, okay, it went from 2 to 7. So that's how we know it lost. Okay, and then our next thing that we do in our mind is to go loss of electrons is oxidation. Okay, so that's Leo the lion. Um, and once you figure out Leo or oil, you'll know the other thing is Rig or Gur. So this is Mn 2 plus. And again, oxidation means our electrons need to be on the right side. Don't worry about water or anything else. Just look at these two. And this is what I meant on the first slide by just write what you know. Okay, and we're gonna get the rest from our SRP table. So we're just gonna write this. Um, Mn and then arrow the permanganate ion plus electrons. I don't know how I guess it's 5 electrons. This may or may not match what's on the SRP table. It doesn't really matter as long as we know that this on our SRP table will be on the product side because this is our oxidation half reaction. And this, we're going to find this on the reactant side. As long as we know that that's what we need to look for, then we're good. We don't need any other information. So our reduction half reaction is going to be the per iodate ion, and the iodate ion on the other side. So we know that this is some number of electrons. We don't know how many, but we actually don't really need to know that number. We could figure it out, but why do all that work when it's already on the SRP table? So I'll show you how this works. So IO3 minus. Okay, don't worry about the water. We're going to figure all that stuff later. So we have enough to go off of to check our SRP table. So let's go ahead and look for this. So we're going to look for this. We're going to look for this on the reactant side. Okay, so some permanganate ions and some electrons. So let's check this out. Let's erase what I had before so we don't get confused. Okay, so permanganate ions and electrons with the permanganate. Okay, so this is a potential, right? We have the permanganate ion and then we have electrons. But if we look at the product side, it makes um, manganese oxide. It makes manganese oxide. So let's look back at our reaction, and we do not have manganese oxide. Okay, we have manganese 2 plus, so we need to find that on the product side. So this is not it. Okay, this is close, but this is not the one we're looking for. I think we could do better. Okay, so here we have the permanganate ion, and then we have the manganese the manganese ion on the product side. So this is our reaction. It's number 9. It's this one here. And remember, we have the reverse of this, so we need to change this number here. So we need to make this negative. So EOX is negative 1.51. Okay, let's go ahead and write this out. So EOX here is negative 1.51. And actually, I'm going to go ahead and write that whole reaction. So I'm going to copy from the SRP table. So I'm going to kind of like fill in the blanks here. So that was, if we have our reactions numbered, that was reaction number 9. So it's the reverse of number 9. Okay, so I'm going to go ahead and copy that whole thing, the reverse of it. Erase some of this so I have room. So I'm going to write Mn2 plus 4 H2Os. And as a matter of fact, I'm not even really thinking right now. I'm just literally just copying this, or actually the reverse of this, from reaction number 9. So MnO4 plus 8 H pluses plus 5 electrons. Okay, so that's my full half reaction. Okay, let's check my other reaction. So I need to look for this and this. Okay, so that one's going to be, okay, so we need to find IO4 minus ions. Okay. And actually, since this one is negative 1.51, and this is spontaneous, so we need to have a positive E cell. Our only possibilities have to be higher than reaction number 9. These are the only ones possible for oxidizing, because we need to oxidize the Mn2 plus. So these are the only ones that result in a positive E cell are these. Okay, so we know that to look at any of these is not going to work. So we shouldn't even bother with the rest of this table here. So in fact, it's actually number 8. It's right above it. It's IO4 and then IO3 is right above it. So this is it right here. It's number 8 and a positive 1.60. So I'm going to actually copy this to get my half reaction, to get my full half reaction. Okay, so I'm going to copy this. Exactly what I see on here. 2 electrons plus 2H plus IO4 minus makes IO3 minus plus H2O. And my reduction half reaction is a positive 1.60. Okay, so now I need to balance my electrons here. So in this one I had 5 electrons, and in this reaction I only have 2. So the number that they have in common would be 10. So I'm going to take this whole thing and multiply it by 2, and I'm going to take this whole thing and multiply it by 5 so that they balance. All right, so and I'm going to kind of like put everything together at once here and then cancel out everything that's similar. So we have 2. I'm going to distribute this 2 to everything here, just like you would in math. 2 plus 8 H2Os. And now I'm going to put all this stuff over here with it. So 10 electrons plus 10 protons plus 5 iodate ions creates, and now I'm going to write all this stuff. So 2 MnO4s plus 16 H pluses plus 10 electrons plus, and now I'm going to write all this stuff, 5 iodate ions plus 5 H2Os. Okay, so let's go ahead and see what cancels out here. We have all of these waters will cancel out, and then this one will reduce to 3. Um, all of these protons will cancel, and this number goes down to 6 because we had 10 and 16. And then, of course, which is the whole reason all this stuff is happening is because we balance the electrons. So this cancels with this completely because that was the whole purpose of doing this, was to get those balanced. So I'm kind of doing all the hard stuff first, and then I'll get E cell and delta G. So my overall reaction after all of that is this. So I'm going to kind of like simplify everything. 2Mn 2 plus 3 H2Os plus 5 IO4 minuses plus 6 protons. You guys are gonna have to forgive me. I picked a really nasty one. This is about as this is about as psycho as one of these can get. Is this one here? So I did it on purpose because I figure if you followed along on this, you could do any of these. I have a feeling. So 5. That's why I picked this one. Okay, and then that's it. So that's the overall reaction finally. And then my E cell is going to be 0.09 volts. Okay, and now I'm finally ready to calculate delta G. So it's negative 10 moles of electrons times 96,485 coulombs per mole of electron times 0.09 joules per coulomb. Okay, so this number cancels, this cancels. Okay. Let's see if I have an answer for you. I get negative 87 kilojoules of free energy for my answer here. All right. So I have one for you guys to try. It's on the next slide. So it says chlorine dioxide, which is produced by the reaction, sodium, uh, let's see, what would that be? Sodium chloride and chlorine gas make 2 moles of chlorine dioxide and sodium chloride. So this has been tested as a disinfectant for municipal water treatment. Um, so calculate E cell delta G at 25 degrees for the production of ClO2. I will give you one hint here that makes this, because this is kind of given. This is aqueous, and this is known to be soluble, and this is aqueous, so this is known to be soluble. So we should rewrite this in net ionic form. So this would be let's see, two chlorite ions plus chlorine gas makes chlorine dioxide gas plus two chloride ions here. Okay, so see what you guys can do with this one. I don't believe it's as wild as the example I just tried, so hopefully it won't take you too long to do this one. And let's see what you come up with. That's the end of our tutorial.